the respected dignitaries, my colleagues, dear participants, and all the viewers who are watching this webinar live from the YouTube channel. It gives me an immense Shri H.D. Devegowda Government First Aid College. I am Dr. Vijay Kumar, and I have with me my colleague, Mr. Darshan. The two of us will moderate this webinar. Graph theory is the study of graphs, which are mathematical structures used to model pairwise relations of objects. A graph in this context is made up of vertices, which are connected by edges. Few research fields can trace their birth to a single moment and place in history. Graph theory can. Its roots go back to 1735 in Königsberg, the capital of Eastern Prussia, a thriving merchant city of its time. The trade, supported by its busy fleet of ships, allowed city officials to build 7 bridges across the river Tegel that surrounded the town. This peculiar arrangement gave birth to a contemporary puzzle: can one walk across all 7 bridges and never cross the same one twice? Despite many attempts, no one could find such a path. The problem remained unsolved until 1735, when Leonhard Euler, a Swiss-born mathematician, offered a rigorous mathematical proof using the graph model that such path does not exist. That was the beginning of graph theory. As time progressed, several other mathematicians, Hamilton, Cayley, Eldous, Kirchhoff, etc., contributed to the development of graph theory. Today, this field of mathematics has found its applications in almost all disciplines: physics, chemistry, biology, computer science, engineering, commerce, architecture, psychology, sociology, economics, linguistics, and several others. Dear all, in this webinar, there are 3 invited talks. Our first speaker is Professor Dr. Ismail Naci Cangül, Department of Mathematics, Bursa Uludağ University, Turkey. Second talk will be by Dr. Senthil Thilak, Assistant Professor, Department of Mathematical and Computational Sciences, NIT Karnataka. Our third speaker will be Dr. Devegowda, Assistant Professor, Department of Mathematical Sciences, Tezpur University, Assam. It is a great day for our department and a great opportunity for all our participants and the viewers to learn a lot from our speakers about the applications of graph theory. Now, I would like to introduce our today's chief guest, Dr. Raju K. George. Dr. Raju K. George is currently the Dean Research and Development, Dean IPR, and Outstanding Professor of Mathematics at Indian Institute of Space Science and Technology, Thiruvananthapuram. He obtained his Ph.D. in Mathematics from IIT Bombay in 1991. He was a visiting professor during the 2002 to 2004 at the University of Delaware, USA, professor and head of the Department of Mathematics at the University Institute of Chemical Technology, Mumbai, and an associate professor at the MS University of Baroda, Gujarat. He works in the area of complex networks, control systems, functional analysis, soft computing, and machine learning, and industrial mathematics. Dr. George has published more than 70 research papers and co-authored a book on ordinary differential equations, principles, and applications, Cambridge University Press. Dr. George's Eldous number is 4. On behalf of the Department of Mathematics, Shri H.D. Devegowda Government First Aid College, and the organizing committee and all participants, I heartily welcome you, sir. Now I request Dr. Raju K. George to give the inaugural address for this webinar. Over to you, sir.
Thank you very much, Dr. Vijay. Respected Principal Dr. J.D. Narayana and other dignitaries in the Zoom platform, faculty members, resource persons, and other participants who joined for this one-day webinar. To all of you, I would like to extend my very good morning. I feel this is a privilege to be in the inaugural program of this one-day program. We know that COVID has caused a lot of difficulty for us, but one of the blessings is that the use of the web platforms like Zoom that in fact helped in organizing various programs of this type, especially a place like in Hassan district in Karnataka, a rural place. This college, Sri Devegowda Government First Grade College, where through the platform we could come together and for the exchange and impartation of the knowledge. So at the outset, I would like to congratulate the Department of Mathematics and the college for organizing such a program. I came to know that this college is very active in organizing several such programs, not only with the participants from India and from also with participants and source persons from outside India, through online media. So, and also I congratulate Professor G.D. Narayana for be instrumental in organizing various such programs and also encouraging the faculty members to enhance the teaching and research. So it's a very positive thing. And the department is very active. I happen to know that Dr. Vinay Kumar and Dr. Vijay Kumar and Dr. Darshan, they are all very active in training their students to compete both in research as well as teaching the students at the international level. And the graph theory is a very active area of research. And we know graph theory. We have three eminent speakers today. One Professor Ismail from Turkey, and other two research persons from India, NIT and Trichy. And these talks are going to be very useful. And graph theory is being now used in various applications. And if you just take Google Map, nowadays everybody is using GPS, Google Maps, and all the graph theory is being used there. The locations are the vertices and the roads are the edges, and this becomes a weighted directed graph. And various tools of graph theory, like like Dijitra's algorithm or Bellman-Ford algorithm, they are extensively being used. And also various search algorithms in graph theory are employed at various levels. BFS algorithm or DFS, that's a breadth first search or depth first search algorithms are being extensively used in various real life applications. If you look at the computer network system, the routing algorithms, the router, every instant the routing table is being updated based on the congestion and the speed of the network. So there also the algorithms, the fastest reaching program is coined by using various algorithms in the routing table by using graph theoretic approach. If you take data science or machine learning, or even in the study of physics, chemistry to study molecules, and physics, looking at the topology of the atomic structure, the graph theoretic tools are heavily employed to simulate the atomic models, especially in condensed matter physics. So various, I named a few, but there are various applications in graph theory which can be nicely used for real life application and as application in research. I hope this one-day webinar is going to be a great success, and it will help the experts and the participants to interact and come up with a very good inspiration to do more research in graph theory. So India is known for its mathematical talents, and we should tap our talents in carrying out the research, and also not only publishing papers, but also taking these papers into real life application. Graph theory is one such where a lot of theory is already available. This can be now taken into applications And as I mentioned, whether it's in Google Map or computer network or in other real sciences or any other application, data science or machine learning, where we can make use of these algorithms and come up with real life applications of graph theory. So I wish all the best and success to the organizers for the conduct of this today's webinar, and very best to the participants. Hope that this webinar will meet its purpose and promote the further research and employing its in the applications. And all the best. Thank you very much, and have a good day and a good interactions and deliberations in the webinar. Thank you very much.
Thank you so much, sir, for your wonderful words and motivating us to organize several such workshops and webinars. So we are very grateful to you. So you have given your precious time for us. Thank you so much, sir. Thank you for joining us.
Thank you. Thank you.
Before moving to the technical sessions, we have a few instructions to the participants. Those who joined the webinar through Zoom, please mute yourself during the session. Participants will be given a chance to ask their questions at the end of the session. The YouTube viewers can post their questions in the chat box, which will be addressed at the end of the session. Our first speaker, Dr. Ismail Naci Cangül, Professor, Department of Mathematics, Bursa Uludağ University, Turkey, has already connected with us. So, sir, welcome to this webinar and our institute online, and thanks for accepting our invitation. Sir, before going to you, we'd like to introduce you to our participants and the viewers. I request Vidya Madam, Department of Commerce, to introduce Professor Ismail Naci Cangül. Over to you, madam.
Thank you, sir. A warm good morning to all. I, Mrs. Vidya, Assistant Professor of Commerce and Coordinator of IQAC, Sri H.D. Devegowda Government First Grade College, Padolippe, take immense pleasure to introduce our today's eminent resource for the international webinar on the applications of graph theory. Dr. Ismail Naci Cangül was born in Turkey on 14th August 1967. His father was a post office officer and his mother is a housewife. He graduated from Uludağ University, Mathematics Department in 1987 with the highest marks amongst all. Cangül completed his first MSc in Mathematics in 1989. After this, he was sent to UK for academic research by a HEC grant, so he has completed his second MSc in Mathematics from Warwick University for the thesis entitled Normal Subgroups of the Modular Group under the supervision of Caroline Series. In 1994, Dr. Cangül obtained his Ph.D. from Southampton University, UK for his thesis entitled Normal Subgroups of Hecke Groups under the supervision of David Singerman and advisor Gareth Jones, where he studied regular map theory, which connects Galois theory, group theory, graph theory, Riemann surfaces, algebraic curves, and moduli spaces. During Cangül's compulsory military duty, which took 16 months, he had been a protocol officer in the main headquarters of the Turkish First Army during 1994-95. Dr. Cangül started his academic profession in the year 1995 with an assistant professor in the Department of Mathematics, Uludağ University. Within 4 years, he was promoted to associate professor in analysis and theory of functions. And finally, in the year 2005, he became a full-time professor in Uludağ University. He has been working in the same department since then. Professor Cangül worked as a Bologna expert for the implementation of university reforms within the team of Turkish national experts for 11 years. He attended over 100 meetings and gave many seminars. He had been in 2 European Union projects on quality culture and institutional review. He had been the supervisor in 3 European Union student projects. He also took part in 17 scientific research projects from TÜBİTAK, Turkish Scientific Research Council, and Uludağ University. Professor Cangül had been the Dean of the Faculty of Arts and Science for 6.5 years between 2008 and 2015. Before that, he had been in many administrative positions, including the Rector's Advisor and International Relations Coordinator. He attended numerous national and international congresses and gave over 200 talks. He organized 8 international congresses or workshops. 2 of these were supported by TÜBİTAK. He also has been in the scientific committees of over 30 international congresses. Professor Cangül has written 49 books, over 640 scientific research papers, half of which are indexed by SCI or Web of Science. His research spans across several areas of mathematics like graph theory, group theory, number theory, discrete mathematics, etc. Google Scholar database shows he is having an H index of 26, I-10 index of 64, with his publications receiving more than 2,800 citations. Most of his scientific works has been completed with around 150 co-workers from Turkey, France, UK, India, Canada, USA, South Korea, Greece, South Africa, Japan, Romania, Hungary, etc. 20 of his scientific papers have been awarded by TÜBİTAK's Scientific Papers Support Program. He had already supervised 15 MSc students and 21 PhD students. Most of his students were supported by scholarship from TÜBİTAK. Professor Cangül had been abroad 3 times with the support of TÜBİTAK and many times with the support of Uludağ University, YOK, and Turkish National Agency. Professor Cangül had been awarded several prizes and awarded as a result of his scientific accomplishments. Some recent ones being the highest number of annual publications prize in the year 2011, the special prize for Bologna Coordination Committee member in 2011, the highest number of annual projects prize in the year 2012, Scientist of the Year prize in the year 2012, the annual Successful Academic Group prize in the year 2012, the highest number of annual publications prize in the year 2013, and the Best Performance Award in the year 2016 in Uludağ University. It is our privilege and honor that today we have with us such an eminent researcher. It's a proud moment to our institute that Professor Cangül accepted our invitation to deliver a talk on some recent applications of graphs. On behalf of the organizing committee and all participants, I heartily thank you, sir, and welcome you to this international webinar on the applications of graph theory. Thank you very much. Over to you, sir.
Thank you, ma'am. Thank you for this nice introduction. I'd like to thank to all of the organizers, especially my friend, Dr. Vijay Kumar Muni, whom I met only 2 months ago during my visit to India. I'm happy to have the chance of collaborating with him in control theory and graph theory in the future. Also, I would like to thank Professor Raju George for nice introduction about the applications of graphs. Today in this event, there will be many eminent mathematicians who will be talking about the applications of graph theory, and they are real experts. I usually work on the theoretical part of graph theory, but of course nowadays only theory is not making governments and rectors happy, because they need money, they ask for money, they ask for applications. Therefore, India is very good in this manner because half of Indian mathematicians, at least half of them, work on applied part of theory. So it's a good country. I follow India very closely because I regularly visit India. On Sunday, I'm coming again to Karnataka, Kerala actually this time. Very often I come. That's why I love India, because it's like my second country, I should say. I love being in India. interestingly. And I like the culture, I like the mathematicians, and I like the friends there. I have lots of friends, so it's always my privilege, not yours, to be with you in your events, hopefully physically most of the time, but this time it was not possible. I just missed it. You are a big country. It's difficult to move from one part to other part. Every time I want to come to India, all my friends all around India, they invite me, but it's not possible each time to visit all the friends. So this time we will be online. Hopefully next time we shall meet face to face with many of you. So I shall start with sharing my screen. Okay. Yeah. I think it's readable. The
Yes,
title
it
is
visible. Visible,
perfect.
yes.
Thank you.
Yeah.
Thank you, Vijay. Some recent applications of graphs. As I study on the theoretical side mostly, and with topological graph indices, which are very applicable subjects, of course, today I will be mentioning about this part. I'm sure there are, I know there are lots of other applications like graph energy and social problems, chemical problems, industrial problems, transportation problems, so many problems from ancient times to our day. Some people know about Königsberg bridge problem, which is supposed to be usually by many mathematicians, by many graph theorists, as the start of graph theory. It was in Euler, Leonhard Euler, Swiss mathematician time, 18th century, the first half of 18th century. This problem was became very famous actually in the city of Königsberg in Belarus, in Russia. So since that time, when Euler generalized this problem and gave a theory, people accept 1736, the year 1736, nearly 300 years ago, as the starting date of graph theory. But actually it goes back, the applications of graph theory goes back to many thousands of years ago. Studying with astronomical things, satellites, the solar systems, this kind of things, people studied geometrical shapes, polyhedra. So graph theory goes back to these years actually. These are the fundamentals. Many people will mention about this, so I will mention briefly for those who doesn't know very much graph theory maybe. Usually we take a graph denoted by G, and it consists of two sets, V and E. V is for vertices, E is for edges. So when you were in your childhood, you must have drawn, every day actually we draw some figures, dots and lines between them, or curves between them. Curves or lines, meaning the edges, they denote the correspondences, the relations between objects. These objects, these dots, could be people, people in a house, people in a school, people in an office, people in a country, people in a network, okay, or neurons in your brain, or companies, or countries. So anything, any two objects, whatever they are, who could be in relation somehow, can be modeled, can be denoted by a graph. This is why graph theory is so popular and so fastly growing every day and every day. Still, there are maybe tens of papers every day written on graph theory. So I will be trying to summarize only, of course, in a short time, 40 minutes, about some applications by theoretical part of graph theory. So usually the number of vertices is n and the number of edges is m. And these two graph parameters are called the order and the size of the graph. So when we call the order, it means 1, 2, 3, 4, 5, 6. This is a graph of order 6. And what is the size? The size is the number of edges, like here, 1, 2, 3, you count them, and this is the size of the graph. And another important idea is vertex degree, degree of a vertex. It is denoted by degree of V, D of V. It is denoted in different ways, of course, in many papers. So the vertex degree is the number of edges meeting at this vertex. For example, this vertex has degree 4 because this curve and these 3 lines are having this vertex as an end vertex, you see? So this has degree 4. This has degree 2 because it is incident to 2 edges here. So this is an easy idea. We should know about pendant vertex. Pendant vertex is also very important, in especially when you study with networks, when you study with trees, this kind of things. Pendant vertices are very important. So let's continue. So already I mentioned a little bit about the idea of modeling by graphs. How we use, this is important, you must understand this if you are new in graph theory. The seniors in graph theory, of course, know everything very well. We have objects, as I listed, as I exampled a few minutes ago. We have the objects with some relation between them. They might like each other, they might know each other, they may import to each other from each other, they may export to each other, they hate each other, they borrow each other, maybe, or they are ordered according to their heights, maybe, or their edges, or their orders in the group. Okay? So this kind of applications, this kind of real life situations can be modeled by a graph. Instead of every person, or instead of every neuron in your brain, or instead of every country, you can take a dot, a vertex, okay? In network theory, people prefer to use the word nodes, okay? There are lots of words. In graph theory, it's a new area, still new area, young area, and the wording is not standard yet, okay? Still, different people uses different words for the same thing for different purposes. So it will be like this for many more years, I believe. So if you model some real life situation by a graph, then instead of some real life situation, some brain network or some communication network or some transportation network or some chemical molecule, okay? Instead of studying these problems in real life, which sometimes needs money, time, laboratory, technical equipments, measurements, experiments, all money and time. Instead of doing this, we study graphs, modeling these real life situations. If you study the model, you have to have some mathematical means mathematical methods, mathematical tools. I will be talking a little bit about these tools today. How we can study some graphs mathematically to obtain mathematical methods and to comment these to get information that we could get normally in the laboratory or in the computer in a long time. Okay, it's expanding a lot of money. So this is the idea, my friends. Many applications, as I listed here, you see, you can find all these in the internet easily. In chemistry, in physics, pharmacology, pharmaceutical sciences, transportation, trade, game theory, social sciences, nowadays networks, city planning, neuroscience. You can add lots of areas. When there are relations between objects, people, things, whatever, then you have this idea to use. Okay, this is very important. Of course, modeling, mathematical modeling is more than graph theory. If you use mathematical modeling, then you use some area of mathematics to solve some real life problem. Graph theory is only one part of this modeling. So everybody must use somehow modeling, artificial intelligence, statistics, and linear algebra. I believe the future is in linear algebra and statistics. If you know, for youngsters, I'm telling this, if you know very good linear algebra, and if you know very good probability theory, distributions, this kind of things, then you will be a very good mathematician, you will be a very good scientist, and you will be very happy, believe me. You will be respected at least by what you do, what you produce in your business, in your research. So this is the idea. We obtain mathematical results by mathematical method from graph. Graph is an object, abstract object. It is nothing. It's not. It's just some drawing we do. We draw in the blackboard or in a paper, in a piece of paper, or in some objects you have in your hands, for example. It may be an orange. You can draw some shapes, some lines, some dots on the orange, or you can draw on a ball. You see, every surface you can draw, you can embed some graphs. Of course, there are lots of types of graphs as well. I will not be able to say later, so I just open a bracket at this point. For example, there are oriented graphs. There are directed graphs called D-graphs usually. There are weighted graphs. There are everyday new types of graphs, not only ordinary, undirected, simple graphs. There are also several other types of graphs because real-life applications have mostly direction or some numbers attached to every vertex or every edge. The length of one street is not the same with another street, or the popularity of someone in a network is not the same with the popularity of someone else in the same network. One may be an influencer, the other is just a new beginner in this network. He has a lot of friends. This one, he has only one friend maybe at the beginning. So let's continue with graph theory. Some well-known applications to count are the traveling salesman problem, four-color problem, Königsberg bridge problem that I mentioned, mazes, puzzles, shortest path problem, Chinese postman problem, These are the first ones when you say graph theory to remind. So I will be giving some ideas, some brief summary, but I want to give you some real application that started modern graph theory, chemical graph theory, approximately 80 years ago, more than 70 years ago. So in the last 7-8 decades, graph theory is growing in this direction very fastly. Molecules, chemical molecules, molecular graphs. These words you must be hearing from time to time in the titles of the papers, books. There are lots of chemical graph theory researchers nowadays. What they do, they have mostly mathematics and chemistry PhD, 2 PhDs. So they know both sides very well, and they apply mathematical methods to chemistry, to molecules. And they obtain mathematical numbers, functions, matrices, graphs, whatever is the tool, mathematical tool, for these molecules. How they do is a nice idea due to Harold Wiener, a chemist actually. He defined this modeling and calculations, luckily, without knowing, in 1947. And later, in 1983, Trinastich, and in 1986, Gutmann and Polanski replaced atoms by vertices for each atom in a molecule, like oxygen, hydrogen. They put one vertex. And if there is a bond between two atoms, then they put a line, they put an edge between these two atoms, okay? So that's how they obtain the molecular graph, a graph corresponding to molecule. Molecule is a very tiny thing. You cannot see it, of course. It's only with electron microscope you can realize what's going on there. So if you draw a graph by a pen and pencil or in a paper, then you can study concretely this graph to obtain results. So this is the idea Harold Wiener used in 1947. For example, this is the plastical model. This is not a natural object. This is the plastic model chemists use to show the ethane molecule, C2H6. Ethane is one of the molecules, second molecule in the alkanes class. Maybe you remember from chemistry classes, alkanes are very important chemical substances. Methane, ethane, propan, butane, pentane, like this, they go on, you remember. CN, H, 2N plus 2. This is the formula. So here C2H6. Every carbon atom, these colored ones, have 4 bonds, 4 chemical bonds. You see, one carbon blue, one pinkish here. They are connected, and this blue is connected to 3 hydrogens. And this pink is also connected to 3 hydrogens and 1 carbon atom. So these are also called carbon molecules. There are other molecules in organic chemistry, but this in organic chemistry, we have mostly carbon molecules. That means the vertex degree is at max 4, nothing more than 4 a vertex can have. So this is the chemical model for ethane molecule, and this is the graph. You see the resemblance, they look very similar. You just delete the words, the letters H and C, and you put some vertices, and you connect these vertices by, instead of abstract chemical bonds, by lines, by edges. So this is the graph. This looks like this figure or this figure more, okay? So this is the idea, very basic idea, but it is so useful, so economic, so industrial. According to FDA, I should say, for example, FDA is Food and Drug Association in US. When you invent, when you have a new medicine, you have to go through FDA regulations. And according to FDA regulations, FDA reports, sorry, one new medicine costs about $5 billion because there are lots of stages up to legislation, legal parts, experiments, animal experiments, theoretical parts, human experiments. There are very important stages. You remember in COVID, when they were searching for COVID vaccine, we heard all these steps. It's in stage 1, it is in stage 2, it's now, they are trying to finalize it in stage 3 like this. So it is very expensive. But if you use mathematics, if you use graph theory in some stages, then you may reduce the cost of having this new medicine. By just mathematical calculations, you can overcome lots of problems, lots of steps. And we can calculate in chemical applications, I should mention, we can calculate, for example, boiling and melting points, molecular weights, atomic weights, density, branchedness is, I shall mention today, isomerization, also I shall mention, reformation, spectroscopic properties, which are related to spectral graph theory, energy and linear algebra part, and many other structural properties of atoms and molecules. So just some mathematical formulae, by means of them, you can overcome complex geometric, electrostatic, quantum chemical methods, which needs lots of special equipments in your laboratory, especially the computation time. So time is money nowadays, you know. The life is very fast. So what Harold Wiener did in 1947, dear friends, he defined, of course, he didn't call, it's not ethical, as we all know, to call something by your name when you invent it. So it's called later, many years later, as the Wiener index. He defined a sum of two parts, actually a formula consisting of two parts which are added to each other to obtain some chemical chemical parameters. And one part was involving this called Wiener index. Wiener index has this strange looking formula. What is Ki and I is explained here, but I shall give you the application directly. Don't think about the formula. Formula is easy, no problem. I shall give you an example so you will understand it. Boiling points and melting points of molecules mainly, this is a well-known fact in chemistry, mainly depends on the branching. Sometimes the molecule goes straightly, like a chain. Sometimes they become very compact, okay? So this affects the melting and the boiling points of these molecules, sometimes isomers. So Wiener index of an alkane molecule provides a measure, this is a well-known fact again in chemistry, of the branched structure, and comparing the isomers, comparing the Wiener indices of these isomers of some alkane molecule, we obtain, we can compare the boiling points, the melting points of isomers of some alkane class, for example. I will give example. This is just preparation. Isomers, just to remind you, have the same molecular formula. So mathematical formula is the same, C5H12, for example, but they are ordered, the atoms are ordered in different figures, different orders, okay? The arrangement of the atoms are different. So this affects some chemical and physical properties, but some of them doesn't change. The boiling point is our point. So boiling point is affected by this order. My example is like this, very famous example. Pentan, penta, you see, like pentagon, 5 in Latin. C5H12, this is one of the alkanes, like ethane molecule before. You see, there are 5 carbon atoms and 12 hydrogens around them. In the second one, 4 carbon atoms are ordered in a line, and one of them is branched here in the third one, okay? Of course, if you take the mirror reflection, then it could be the second one as well. So from the second or third one, you have a second branch, so you have a Y shape there, okay? Here, carbon atoms do not have any Y shape, okay? This is the difference. And the third one, called neopentan, after pentan and isopentan, neopentan has a plus shape. 5 carbon atoms are 1 at each corner and 1 in the middle. You see that? You see in the screen, 5 carbon atoms, and again, around them, they are surrounded by 12 hydrogen atoms. So, my friends, these are all the same. Now, you have a factory. You are a factory owner. And you need to boil every day for some textile application or some detergents, for example, for some chemical application of chemistry in real life, you need to boil some pentan. And there are 3 choices for you. Of course, this is for pentan, 3 isomers. If think of 20 carbon atoms, 20 carbon atoms could be very linear, 20 of them in a line, or very compact. In between, there are lots of choices, lots of isomers, billions of isomers sometimes. So 3 is easy to compare. But if you have billions of isomers, to find the best one, best economical one, you need computer, you need mathematics. You cannot do billions of boilings, okay? So, my friends, now how we calculate this index, Wiener index in chemical graph theory? We start with the first carbon atom. Just follow the screen, the cursor here. The first carbon atom, and you calculate in the first bracket, you see, the distances between this carbon, this first carbon on the left, and the other 4 carbon atoms. From first one to second, the distance is 1, plus. From the first one to third is 2. Distance is the shortest part, the length of the shortest path, okay? So from this carbon to this carbon, there's actually only one way. So, but in any graph, it could be more than one way, different ways, okay? From one city to another, there is normally one road, but there are other roads as well, okay? So this is like this. So 1 plus 2 plus 3 plus 4, this is for the first carbon atoms. So we delete now this first carbon. We continued with the second one, the second bracket. From the second to third, the distance is 1. From the second to fourth, and from the second to the fifth. So 1 plus 2 plus 3, which is 6 here. So we delete the second, we continue with the third one in the middle. Only carbon atoms. You can do the same with hydrogens, but you need to do more work. So no need. Just this is called the carbon skeleton of the molecule. So from the third one to fourth is 1. From the third to fifth is 2. So this is the next bracket. And from the fourth to the fifth, there is distance 1. So my friends, this first pentan molecule, okay, the first isomer, ordinary one, has this number equal to 20. What about the other two? You see, this is the Wiener index of the linear one. You may say that this is not linear. This is like a bird. This is like an M letter M. But chemists use this nice idea. They don't put the vertices. Vertices are placed in the corners only, okay? So this is a very genius idea. They just draw some line, broken line, and you can count the number of carbon atoms. 1, 2, 3, 4, 5. This is actually linear, but they just give a movement to it to understand the number of carbons. If they draw a line, you would not know there are 5 carbon atoms, okay? This is very genius idea. The others are like this. So the numbers are obtained as 18 and 16. You can count if you wish. Don't worry. The same thing will happen. And what about the boiling points? The boiling points for this special pentan is 36 centigrade. This isopentan, it is 27.9, and the neopentan has boiling point very low. Economically, which is best, of course, which is needing less energy to boil, is neopentan. So that means, for chemists, if you are using some carbon molecule, especially alkanes, instead of linear structure, you must have very compact structure to boil easily without spending more energy, okay? This will spend 3 times, this will spend 4 times more energy, probably. I don't know if there is linear relation between them. So this is the idea. This is the regression between boiling points and Wiener indices. Wiener index is high, means boiling point is high. So you look for the molecules, the isomers with less Wiener index, smaller Wiener index. Okay, towards the end now. Now this was the chemical applications, my friends. Now I shall briefly mention about other applications and complete my talk with your permission. Networks are everywhere indeed, everywhere, in your mobile, in your computer, you are always connected. Your family is a network. Your apartment, if you are living in an apartment, is a network. Your street is a network. Your schoolmates, teachers are a network. Okay? We are living in networks. We are using them to communicate, to socialize, to popularize. Okay? Everybody likes to be popular. Everybody likes to be getting likes of others in networks. For youngsters, this is a real problem nowadays. Social media applications that I mentioned. Communications is, of course, necessary. Without communication, I don't know how hard it would be. Before the mobile phones, sometimes we joke around us, and we say how we were living without mobile phones. Now we've forgotten those days, of course. Transportation is a network. In a city, you must have good transportation system. For this, you need mathematics. Okay, you need different areas of mathematics. City planning is all mathematics and graph theory. Neuroscience, maybe I should open a bracket here, parentheses. Neuroscience, some very advanced topic. Now they study with little organisms, very little organisms, very basic, not like human beings or animals. So neuroscientists deal with neurons in your brain, in your body. Neurons have synapses, electric shocks between them. And learning is like this. Learning, when you have some neurons stretches some synapses, some electricity around. And when they meet the other networks in your brain, then learning starts. This is how they explain. Also, for the illnesses, you may be watching in the space movies, sometimes the alien injures the space officers, spaceship officers, astronauts, whatever, and they go to some machine, they just lay back, okay, lay down back, and the machine starts to operate their body after pushing a few buttons. You see, this is artificial intelligence. It would happen. It is happening nowadays. When you enter, when you get on your car, it says 7 kilometers to your house. The traffic is, this line is red, so don't take this line. It gives you suggestions just when you start the engine, okay? In your mobile phone, there appears some messages. This is all artificial intelligence. This is counting on your experiments, using probability and giving you the best choices. It is very good for life, for the quality of your life. So in the future, it will be very much more in our lives. But the main question is, will they get over us humans? The machines will get the world? No, I don't think. It's not possible. They don't have a soul. They don't have a soul. They will not have a soul. So they are just some things that we produced. So they are limited. Humans are not limited. They cannot use their limits. We cannot use our brains, for example. Only 7% of our brain we can use in average. But machines are more limited. They can maybe more, they can do more than human beings. They can be very fast in calculating several things. They can see maybe kilometers away, okay, like telescopes, they can see the space. But human beings will not be unuseless, never. This is my idea, of course. So neuroscience is very important in that sense, and many illnesses will be solved by the study of neuroscientists in the near future. These are networks, these are examples of networks comprised of nodes and edges between them. So each node represents an entity in the network, and each edge represents some connection. Usually they know each other, they like each other, whatever is the word, the connection. This is the network connections, not the persons, networks. So, for example, here, this purple area, pinkish purple area, is very intensive area that the big networks are placed. This is in year 2014. I couldn't find a more recent one. Probably they have not published one later. This was the devices in the internet, the servers in the internet in 2014. This is neural networks. I mentioned a little bit, so the time is finishing. Social networks are also very popular. You see, this is a graph. Instead of every lady and gentleman, you put a vertex. You see that they know each other. They are connected to each other. For example, this one has lots of connections, for example, 1, 2, 3, 4, 5, 6 at least. But this one, for example, has 2 connections only. So this is new in the city or in the company. So this shows you the popularity, the range, the rank, lots of things about the people, about the companies, about the countries. Transportation, no need to mention, everywhere, metro, train, bus system, they all operate in the city from time to time. The distance is not too important usually, but the connections from this station where I can go if I take this line, okay? This is important. Of course, sometimes we put directions, as I mentioned before, but I don't have time for this. For directed graphs, usually in communication, directedness is needed because someone might like each other, another one, but this one does not like this one, for example. So sometimes it is one way, like a road. Some roads are one way, some roads are two ways, okay? So adjacency matrices are used, for example, to calculate some properties. Linear algebra, spectral graph theory is used for communication networks as well, and for ordinary graphs as well. Adjacency is very important. If two vertices are connected to each other by an edge, then they are called adjacent. This adjacency gives you 0-1 matrix uniquely. So it's a symmetrical one usually, but in directed networks, it's not symmetrical, as you can see, okay? According to the diagonal, main diagonal. So calculating the eigenvalues, you get some energy, graph energy, which is also very important in physics, in chemistry, in engineering. Graph energy, intermolecular energy. So these are kinds of networks you can find in the internet. Metabolic networks for biology, for zoology is very important. All these networks are there in scientific and daily calculations, daily applications. How we study real life situations, just I'm finishing, by means of graphs. There are several ways. Some of them, the main ones are graph matrices, topological graph indices, and some other graph parameters like eccentricity, like diameter, like independence number, whatsoever. By using these ideas, mathematical parameters, we can obtain information from the graph you have, which models real life situation, okay? So commenting on these numbers, like 20, 18, 16, we obtained by Wiener index, we can compare real life. We can obtain some real-life information. So, by means of graph matrices, there are more than 100 graph matrices, especially adjacency matrix I already mentioned. There are incidency, Laplacian, Zagreb matrices, lots of matrices there are. For each one, you can define some energy, you can calculate some energy parameters, and you can obtain different properties of chemicals or others. Energy is this, I shall pass this. Graph matrices, some of them are listed here. Topological indices also, there are more than 3,000 topological indices, like Wiener index, a formula you have. This is called the topological index. It's about the topology, as Professor Raju said, the topology of the graph, and it gives you some ideas from the topology, from the ordering of the vertices and edges, some new ideas. So these are all indices, and there are lots of nowadays Indian mathematicians giving their names. Their names are given actually to the topological indices like VL index, Banhati index, lots of them. People in mathematics, for youngsters, what we do when we are stuck in some topic, we do the varieties, we calculate the varieties, we define them, and we study them. For example, if you stuck with some formula, additive formula, you study with multiplicative versions instead. Mathematically, you can always study this, but application, I don't know. It may have some applications, it may not have some applications. You might study reduced versions, modified versions, co-index versions. You see lots of versions of the classical versions. Like geometry, you have Riemannian geometry, Riemannian manifolds. Then people study semi-Riemannian manifolds, for example. Just putting some word, like fuzzy algebra, fuzzy topology. So graph parameters are many to count, no time left. So I think I should stop here by thanking you for listening to me. I hope I could give you what theoretical mathematicians understand from applications of graph theory. As I said at the beginning, there are many eminent speakers in the list. Today they will be talking about the real life applications. They know better than me, of course. But for the theoretical part, I see the picture like this, and I see the feature in graph theory. So for youngsters, of course, lots of areas of mathematics nowadays, like control theory, like artificial intelligence, like the other very popular areas of mathematics. Graph theory is always there. Graph theory is always in our lives and in our studies. So don't become a graph theorist, but at least you have the basic ideas of graph theory, because one day in your research, some small piece of information may help you to finish your PhD thesis, to obtain a nice formula instead of a long, very complicated formula. Okay? So this will happen in your lives, and I wish to young listeners especially best of luck in their future, and to the seniors, thanks for listening my talk. Thank you.
Thank you very much, sir, for this wonderful and exciting session on the applications of graph theory in several disciplines, especially in chemical reactions, the social networks, artificial intelligence, neural networks, etc. So we enjoyed a lot by listening to your session. Now, if your permission is there, so we'll go to the question and answer session. So first, we will take some questions from the participants who have joined through the Zoom app. Those who wish to ask the questions can unmute themselves and raise the questions. Those who wish to ask the questions can unmute themselves and raise the questions. We have received some questions in the YouTube channel also. Tanga Rajeshwari, she asks, in slide number 5, vertices and edges created for hydrogen atoms. Generally, hydrogen atoms are not considered for molecular graph. Is it correct or not?
Both actually, it's correct and incorrect. If you want to shorten your calculations, you just do the calculations with carbon skeleton, carbon atoms. This is enough. But if you add the calculations for hydrogens as well, then you get bigger numbers, and all numbers get bigger. So the comparison does not change in terms of Wiener index. So instead of adding the hydrogen atoms, they prefer to do calculations for just carbon atoms, which is called carbon skeleton of the molecule. So it's a nice question, and it's enough to do for carbons. For other applications, maybe we need to, for some graph parameters, for example, you need to calculate all vertices, of course, in the network or in the molecule. But for these calculations, we just, it's sufficient to have the carbon atoms only. Thank you.
We have one more question. What about the double bond compounds in graph theory? Asked by Mr. Shabir.
Can you repeat? It's gone a little bit. Can you repeat the question?
What about double bond compounds in graph theory?
Double point.
Double bond compounds.
Double bond. Yeah. That's a discussion. There is a nice question, very nice question. If you study with matrices, then you have to put ones and zeros in, for example, adjacency matrix. this vertex is joined to this vertex, for example, by this bond. Then you put, this is vertex V2, this is vertex V4, for example. So the matrix, adjacency matrix, will have A24 and A42 entries as one, because 2 and 4 are connected to each other, okay? So A24 and A42 symmetrically in the matrix, they are put 1 instead of 0. So if you have double bonds, some people take still 1, because in graph theory, the important thing is, are these vertex connected, is this vertex connected to this vertex? This is important, the distance, the connection length. Normally, this is not important in classical graph theory. So they put 1, but in calculations with spectral polynomials, for example, I believe that it's more practical to put 2 in for double connections, for double bonds. If this connect, for example, this is oxygen, and these 2 oxygen atoms are connected normally by 2 bonds, 2 chemical bonds. Then for the matrix, for this entry, I put 2, for example. Otherwise, you get wrong parameters, you get wrong result. But there is still lots of discussion. Some people use 1, some people use 2 for this. Very nice questions. Thank you.
So our third question is asked by Deepankar Chaudhary. Sir, can we calculate the Wiener index for cooling point of a liquid?
I think so. I'm not a chemist, but I know just the application in alkanes. Alkanes are carbon molecules, and as far as I know, for all carbon atoms, you can do. For fluids, I think it should be similar, but I am not completely sure. They may try. If they correspond, they calculate the Wiener indexes, which is easy. They just draw the chemical model of the fluid, whatever it is, the chemical compound. They can calculate these numbers, and for boiling points, for example, they can compare if this is the same order or the correlation is different. One is increasing, one is decreasing maybe. For Wiener index, for alkanes, it's always the same order. The highest one corresponds to the highest one, the lowest one corresponds to the lowest one. But in different applications, this may be different. So nowadays, lots of graph theory papers dealing with indices, they are published and they say, this is good, this new index, this modified new index is good for boiling points. This is for atomic weight. So everybody has different applications. This is the richness of mathematics and graph theory. So they may try to go for it. Probably it's the same. I don't know, but I have no experiments or no knowledge.
That means it will open new areas in graph theory itself.
Yeah, sure.
Yeah. So our fourth question is asked by Behra Rupashri. What are the graph parameters that can be related to topological indices so that it can be applied to molecular graphs?
That's a big question. Lots of papers can be written on this here. Of course, topological graphs, molecular graphs are important, naturally. Everybody accepts this. And there are more than, as I said, 3,000 topological indices. For each one, you can write a paper easily. For each molecule and for each index, you can write a paper. Nowadays, sometimes there are very basic papers coming to me for reviewing. They just calculate the indices, mathematical formula, very basic formula in terms of vertex degrees or edge degrees, edge partition, to give you some mathematical results for some graph classes or for some molecular structure like nanocones, nano shapes, nanofigures, or molecular structures, chain structures, this kind of things. the youngsters must be very careful about this. I mean, it is so easy to produce new papers, but you must do good papers as well, not only very basic level papers. You must sometimes produce good papers because your name will be remembered if you have good papers, not ordinary papers. So you can use these parameters. Any parameters can be used, but it is related to what you want to do. It's related to your aim. You can use, for example, independence number of the graph. Sometimes this number might help you to get idea about some chemical property. You don't know. But these are all open problems, many problems, and it's a very general question. I cannot talk more, but it's nice question. All questions are very nice. Thank you, the participants. That shows the quality of the talk. Usually I have no questions in many of my talks, so I'm happy to answer these questions.
We are receiving a lot of questions by the participants. So we will take a few more questions and we will end up the session. So the next question is asked by Farah Ashraf. She asks how topological indices can help in the discovery of new drugs.
The new graphs, they are not, the discovery of new graphs are not related to topological indices, but topological indices, you use them to calculate you calculate the topological index is a formula, which is a formula for some molecule, for some graph, for cyclic graphs, for example, for acyclic graphs, for trees, for networks. You calculate them. The important thing is to use this obtained information, obtained number, obtained formula, obtained function, obtained vector, whatever is it, to give you idea about real life. Like molecular example I gave, the numbers 20, 18, 16 correspond to 36, 27, and 9. There is no linear relation, but the increase and decrease is the same order. So we obtained that. We can use this idea for larger molecules, because if they are compact, they boil easily. If they are like a chain, all the carbons are ordered, then it is difficult to boil this molecule. This is the idea, for example, to generalize, starting with some smaller. But the topological indices do not help you directly to produce graphs. They are there to calculate for the given graphs. Okay, you must select the correct graphs. If you work for nanoparticles, then you must use some molecular shapes like nanocones or nanospheres. These kind of figures there are in chemistry. So if you use these graphs, then you use the correct topological indices, the right ones, to get the correct information. But not in the first try you obtain. There are many, many, many ways, so you must find the correct way. It's not the easy choice.
So the next question is asked by Mohammad Rafiq. Sir, how can we deal with the infinite graphs in real-world applications? Because we always deal with finite graphs in theory.
Yeah. This is what we prefer. Infinite graphs are difficult to study, to handle, because even if you use computer, infinity is difficult to handle. Infinity is what we need to understand the God, creation, everything. Mathematics, maybe someday, after we pass some line, will help us to understand everything, but not now, not for us, not for our age, of course. So it's some deep subject. So infinity is always difficult to handle. You know, mathematicians handle infinity very nicely. For example, I teach some example in my number theory courses to my students, third-year students in BSc. I give them Euclid theorem. Euclid gave some proof 2,300 years ago. Okay, very long time ago. Before zero, before the place system, number systems are there. Euclid gave the infinity, the proof of infiniteness of primes, for example. So infinity is very important. How he handled, he said that instead of infinity, if we have finite number of primes, what happens? So he couldn't deal with infinity because mathematicians, okay, we are good creatures, better than ordinary people in thinking, but still we don't have the power to deal with infinity. So infinity is always difficult. It's a taboo for most of us. If we deal with infinity, if we have to, we go on around it. We take, if it is finite, what happens? And if we get contradiction, then we say, okay, it's infinity, but I cannot count it. It's not possible. Like here in graph theory, we don't like infinite graphs, but actually in my, as Rafik said, it is not possible to have only finite graphs in the real life applications. The numbers gets very high. Of course, in real life, infinity is not possible. Still, we have finite but very large graphs. But for infinite graphs, nobody dares to study with infinite graphs nowadays because it's really difficult to study. You cannot carry it to computer. You cannot compute anything. You cannot handwriting. You cannot calculate anything. So it's difficult. Normally, you don't need infinite graphs as well in many real life applications. So if you need, then you make a limit, and if you work with this large models and you take the limit case, maybe it's possible. But even in the networks, there are only finitely many, very large, but very finitely many nodes, vertices. So normally we don't need infinite graphs. But if you need, then you must have some limitations. That's what I think.
So thank you so much, sir. We have received so many questions, but because of our time constraint, it is not possible to answer all the questions. But definitely, I will take all these questions to you personally later after the finishing of this webinar, so that our participants will get the benefits from that. So hope that our participants enjoyed this session and they got a lot of knowledge by attending your lecture. So thank you once again for accepting our invitation, and thank you so much, sir.
Thank you very much. Thank you.
Thank you so
Have a
much,
good event, and I hope young people, especially young friends, will get most of it. And I suggest them to attend these conferences, these meetings, because in every talk, even it is not their topic, their area, they should listen, and they will learn a word that might change their future. So this is very important for young people.
Yeah.
Thank you. Thank you, Vijay.
Thank you, sir. Yeah, thank you so much, sir. Thank you. Hope that our young students will get the motivation to join the research career in this graph theory. Thank you so much, sir. So dear participants, our second speaker of today's international webinar is Dr. Senthil Thilak, Assistant Professor, Department of Mathematical and Computational Sciences, NIT Karnataka. She is already connected with us. So, madam, welcome to this webinar. On behalf of all viewers, I thank you once again for accepting our invitation to speak at this webinar. Madam, before going to you, I request Ms. Pallavi, madam, Department of English, to introduce to our participants. Over to you, Pallavi, madam.
Thank you, Vijay, sir.
Thank you for the invitation. Hope I am audible.
Yes, ma'am, you are audible.
Yeah, fine.
Good afternoon. I, Pallavi Ilkal, Assistant Professor of English, welcome all the participants to this session once again. With pleasure, I take this privilege of introducing the esteemed one of the resource persons of the session, Dr. Senthil Thilak, Madam. Dr. Senthil Thilak, Madam, completed her MSc in Mathematics from Sita Lakshmi Ramaswamy College, Tiruchirappalli in 2005. And in the year 2006, Madam completed MPhil. Her work is titled On Energy and Laplacian Energy of a Graph. She was awarded Ph.D. in the year 2013 for her research on some graph theoretic approaches to clustering algorithms and a hybrid cluster-based routing protocol for mobile ad hoc networks. Dr. Thilak taught at several institutions such as the Prime Academy Tiruchirappalli, Mookambigai College of Engineering Pudukottai, NIT Tiruchirappalli, NIT Karnataka, etc. Having an experience of handling several courses to the PhD, MTech, BTech, and CS students. Her list of courses include Advanced Graph Theory, Analysis and Design of Algorithms, Foundations of Machine Learning Algorithms, Mathematical Foundations of Computer Science, Probability and Statistics, Discrete Mathematical Structures, Numerical Methods and Applied Statistics, Data Analysis for Management, Calculus of Variations, Linear Algebra and Matrices, Numerical Techniques, Information Technology, Engineering Mathematics, etc. Several of her courses received a feedback score of 9 out of 10 by the students. Currently, Madam is working as an assistant professor in the Department of Mathematical and Computational Sciences, NIT Karnataka. There, she has supervised 2 PhD students, 4 MTech students, and 44 MCA students. She is currently supervising 4 students towards the doctoral degrees and 2 students for their MTech. Madam's research spreads across algorithm graph theory, frame graphs, wireless ad hoc networks, vehicular network communication, graphs in biomedical applications. She has published 20 research papers in several international journals and conference proceedings. She has delivered over 15 invited talks at national, international conferences and workshops. Dr. Thilak's administrative experiences include the following. She was a member of Research Performance Assessment Committee for 4 PhD students and 2 MTech students at NIT Karnataka. She is a secretary of Departmental Postgraduate Committee, Departmental Undergraduate Committee, Departmental Academic Appeals Board at NIT Karnataka. She is a reviewer, co-editor, and member of advisory committee of different international conferences and journals. It's a privilege and honor that Dr. Senthil Thilak, Madam, has accepted our invitation. She'll be talking on graph theory in brain network analysis. On behalf of the organizing committee and all the participants, I heartily thank you for accepting the invitation and welcome you, ma'am, to this international webinar on the applications of graph theory. Thank you very much.
Thank you, madam. Thank you for the nice introduction. Yeah, and first of all, I'd like to thank all the organizers, especially sir, for inviting me, and it's a nice opportunity to interact with everybody. Shall we start with the session, sir?
Yes, ma'am. Yeah.
I'm not able to share the screen. It is disabled.
So below there is an option called share screen.
Yeah, it says host disabled participant screen sharing.
Yeah, now you can try.
No whisper, madam.
Ma'am, is there any problem? Dear participants, wait for a few minutes because of technical issues. Madam is going to join soon.
Okay, sir. Okay.
Yes, ma'am. It is visible, ma'am.
Sorry for the delay. Actually, there was some preferences that had to be made. Yeah.
No issues, ma'am. No issues. Thanks so much.
Good afternoon, all. Yeah, as you all know, like my topic for discussion, today's discussion is graph theory in brain network analysis. Yeah, so as we know, there are multiple domains in which graphs can be applied. For this discussion, I have chosen one such domains, namely brain network analysis. And at the outset, this is the overview of my presentation. Initially, we'll have a very, very brief introduction to graphs, just look into the definitions of graphs and so on, and a brief introduction to brain networks. Then we will see how we can relate graphs and brain networks. And then we will see how to incorporate network science in the corresponding graph, and how to study the properties of brain networks. And finally, as an illustration, we will look into one of these special methods called graph kernels, using which you can analyze one of the brain disorders. Yes, to begin with, we have these following questions in our mind. What's a graph? And why to study about graphs? So we'll start our discussion with an answer to these two questions. First, what is a graph? A graph, if you look at as a very informal definition, or in the layman's definition, if you see, a graph is basically a diagram of dots. Sorry, there is a typo. Diagram of dots and lines. So wherever you have a picture which involves some dots and lines, that can be interpreted as a graph. So in formal language, we define a graph as an ordered pair VE, where V is always denoted to represent, V is used to represent a non-empty set of elements, which we refer to vertices in the language of graph theory, and in the language of networks, we call that set as nodes. E is referred to as a set of elements called edges. And in the, in the perspective of, from the perspective of network, we refer to that as a set of arcs or lines and so on, which are used interchangeably even in graph theory as well. So as an example, this is a diagram where you have a graph. Here you can see that there are some numbers 1, 2, 3, 4, which are encircled, and these stand for vertices. And that collection is referred to as vertex set. And the collection of all links between pairs of such vertices is referred to as an edge set, as we see here, E1, E2, E3, E4, or edges. Now, in general, when you are trying to draw a graph, there can be orientations over each edge, or the edges can be non-oriented. That is, you can specify directions, like whether the link is from 1 to 3 or it is bidirectional. Okay. So when you have unidirectional edges, the corresponding graph is said to be directed. And when the edges are bidirectional, then the corresponding edges, the graph is said to be undirected. Now, if you look into the origin of graph theory, actually, the field itself started with an application. Like in the earlier 17th century, there was a famous mathematician by name Leonard Euler, who was trying to solve one of the famous problems, namely Königsberg Bridge problem, which is the problem of starting from one of the land areas. There are, like as you can see in the figure on the left, there are 4 land areas which are connected by means of bridge. If you start from one of the land areas, you have to cross over each of the bridges exactly once, and you should return back to the starting point. That's the question. Now, people were trying to solve that in multiple ways, but Euler's thought was to convert it as a graph, to model it as a graph. That is, he interpreted all land areas as vertices, and two land areas which are connected by a bridge are represented by means of a line between them or a link between them. And finally, he proved that the problem doesn't have a solution at all. So this is the origin for graph theory. As I mentioned earlier, the field itself is developed with an application. And where do we use graphs? In our daily life, if you see, almost everywhere, wherever you come across objects or entities between which there is a predefined relationship, you can always associate a graph with that. So as some examples we can see here, these are some of the domains where we are using graphs. Very minor collection of domains where we are using graphs. Like if you want to look into the network of research groups, we can represent it by means of a graph. Like if you take two researchers, if they have a common publication, we can join them by means of a link. And brain networks, internet of network, network of internets, like chemical compounds, network between chemical compounds. So like this, precisely if you want to say where can we use graphs, or if you want to answer the question where can we use graphs, almost everywhere where you have defined a set of objects between which there is a predefined relationship. So basically, when you want to convert a real-time scenario into a graph, there are two aspects which you need to think of. One is, what is your vertex set? So as we defined a graph in terms of the two parameters, namely V and E, we should basically associate the vertex set with the real-time entities. And if you are able to have a defined relationship between a pair of entities, that relationship defines your edge set. So that's how you start relating a graph with any problem in daily life. Okay. Like it is related everywhere, like starting from static network to dynamic network, you can use graphs. Now, these are all examples where you have static networks. Now, here I have given you an example of a dynamic network. So this is a scenario where you are using graph for emergency rescue operation. Now, in this case, you don't have any predefined infrastructure. The nodes are just the battalions and the devices or armed forces which are being used for a rescue operation. So when some operation is for rescue process, you can understand that there will be no predefined infrastructure. So in such a scenario, even in such a scenario, we can think of using graphs. We will consider all those components like militants, the armed forces, which are all involved in the rescue operations, can be treated as nodes. If a pair of entities, it can be pair of military officers, pair of devices which are capable of communicating with each other, we can join them by means of a link. Now, what's the advantage of converting into a graph? And the thing is, especially in scenarios of this kind, if you want to establish a communication at an emergency situation, we call it as an ad hoc situation, we don't have any predefined infrastructure. And in order to facilitate the communication without any issue, there should be a protocol followed in order to facilitate the communication. Now, how to design such communication protocols? So in order to do that, we need certain supporting system which can be related to the real-time scenario. And that's how graph comes into picture. Okay, so we can study the structure of any real-time scenario in terms of a graph. Now, as we are saying that any real-time scenario can be studied in terms of a graph, our next question is, like in today's environment, in today's modern world, we are using computers for everything, right? We are very much equipped with artificial intelligence. For everything, we need computers. So in such a scenario, our graph should be understandable. If you want to use our graphs efficiently, our graph should be understandable by our computers. So for that reason, we have alternative representations of a graph. There are three different representations which are commonly used for a graph, namely adjacency matrix, incidence matrix, adjacency list. Adjacency matrix is basically a matrix. Suppose you have a graph with n nodes. This is a matrix of order n cross n, where you have along the rows and columns the vertices or nodes. And if a pair of vertices are connected by an edge, we put an entry of 1, otherwise 0. in the case of graphs which do not have multiple links between a pair of vertices and there is no loop at a particular vertex, then we denote a pair of entries which are connected by an edge by means of an entry 1, otherwise 0. So basically, such graphs which do not have multiple edges or loops are referred to as simple graph, and the adjacency matrix for a simple graph will be a 0, 1 matrix. Similarly, incidence matrix, if you have a graph with the n vertices and m edges, let us say, then this incidence matrix is an m cross n matrix, where you have vertices along either row or column. We can fix one of these for vertices and the other can be used for edges. And if there is an edge which has the vertex as an end vertex, that is, it is an end of that edge, then we call it, we mark an entry 1, otherwise it is a 0. So like this, we can represent a graph in terms of an incidence matrix. Similarly, we can represent a graph in terms of an adjacency list. An adjacency list is basically a linked list which contains, this is a list having n entries, where for each entry you have the list of all neighbors of that. That is, all those vertices which are connected to that particular vertex will be listed in that. Okay, like this, we have a list for each n vertex, and that's how we represent a graph. And all these three representations are commonly used, but the most preferable representations depend on the density of the dense property of the graph. If the graph is very sparse, we go for sparse in the sense the number of edges is fewer than n into n minus 1. Then we go for adjacency list, because we need to process only lesser number of ones in that case. And when the graph is so dense, we go with adjacency matrix or incidence matrix. Now coming back to our main topic, like how graphs are being used for brain network analysis, we'll first start our discussion with some basic introductions to brain network. Especially why graph is being used as a tool. If you see graph, by the way, it is helping us to visualize any complex system in a very structured manner. We prefer to use graphs. So graph plays a significant role in understanding the structure of the structural properties of any complex network, as well as the functional properties of any complex network with suitable modifications. And similarly, if you look at especially our brain network, basically, if you take our entire nervous system in the human body, it's very complex in nature. And since graph is already useful for understanding any complex network system, this is considered to be more useful even in the case of brain network analysis, as our network system is very complex. Now, as you can see here, if you have the brain of a human being, it can be interpreted in terms of a graph. So now the question is, what role acting as nodes, and how do you establish the links between a pair of vertices? So we will just postpone that question a little further. So before that, let us assume what is the human brain made of. So if you look at the figure on the right, you can see that our human brain is basically a network of a structure called neurons. It is basically a network of structure called neurons. What typically a neuron is? So this is how a neuron looks like. It has three important components, namely the center of the neuron, which is called as nucleus. This is called as nucleus. And there is the boundary of the neuron nucleus, you can see, it is called as dendrites. And there is another long tube which we call as axon. And at the end of the axon, you can see that the particular neuron is connected to another neuron through a means of small gap, which is called a synapse. Now, these are the four main units of a neuron which play a specific role, very important role. Now, as I have mentioned here, these dendrites, which are like looking like the boundaries of a nucleus, these are the connecting wires, which help us to connect one neuron to another neuron. As I have already mentioned, our brain network is a network of neurons. Imagine that millions of such neurons are interconnected together. In what way they are interconnected? One neuron is connected to another through the tip of its axon by means of these synapses. That is the gap between this end of the axon and the dendrite, you can see that is called a synapse. So you can have such interconnection of millions of neurons in our human brain. So now you can imagine how complex the network is. We want to study the network. Why especially brain network? We can see that in the functioning of our brain, as I mentioned earlier, these 4 components play a major role. To start with dendrites, dendrites are basically the components of a neuron. It is one of the components of a neuron which accepts input signals. See, for example, when you are closer to heat, your body reacts to that. When you are hearing a sound, your body reacts to that. How do you react to that? You are getting electrical impulses. Electrical impulses are generated and transmitted to multiple regions of your human body. That's what we call as input signals. So dendrites are responsible for receiving the input signals which are sent by other neurons. And these input signals are then processed by via this nucleus. They are processed and transmitted through the axons. That is the long tube which you can see. So transmitted via this axons, and through the synapses, the electrical signals which are processed and transmitted from one nucleus, one neuron, is sent to the next neuron. So that is how we are able to coordinate among the various parts of the body and execute our desired actions. So this is a very precise introduction to functioning of the brain. So here I'll be using one terminology, 2 different terminologies, namely connectomes and connectomics. Connectome is nothing but simply just the wiring diagram. Wiring diagram in the sense the basic structure which explains how the neurons are interconnected. That interconnection diagram is what we call as connectomes. And connectomics is at a particular branch of neuroscience which deals with the study of connectomes, or which talks about modeling of connectomes. Now, graph theory is considered as an analytical tool for connectomics. That is, in the study of connectomes, which is basically the study of brain network, graph theory is used as an analytical tool. What is meant by, why especially the word analytical tool? It is called so because we are able to analyze the entire structure of the brain network, which is highly complex in nature, by using the simple properties of graphs. Okay, which is a boon to the neuroscience department, and we are able to do it very easily with the help of graphs. Now, what is the origin for this application of graphs to this neuroscience or brain network analysis? And if you look at the literature, the graph theory field of graph theory as well as network science, they were used in the field of neuroscience at the end of 20th century, where it took a lot of time to accept this interpretation of neural networks in terms of graph theory and network science. And it happened after the publications by these researchers, Feldman, Van Isen, Young, Watts, and Strogatz. And actually, parallelly, if you see, there was another scientist, namely Raman, who visualized, actually this happened because the neurons were, the neurons which form the basic components of neural networks were studied thoroughly. And the famous scientist, namely Ramon, claimed that neurons are basically discrete cells. That is, you can visualize your neural network, brain network, in terms of discrete components which are interconnected together. And this is the basis to give us an idea, and along that graph can be used, because graph is also basically a structure where you are interconnecting discrete objects, namely the nodes, by means of links. Okay, so this is the basis for allowing graph theory to use as a model for nervous system. And initially, before Ramon identified neurons as discrete cells, there was another study which claims that, another study by Golgi, which claims that neurons are not discrete cells, they are continuous cells. So these two were contradictory studies, but still both received Nobel Prize for their inventions in 1906. But later, with the support of electron microscopy, the invention by Ramon was supported. It was the inventions through electron microscopy supported the findings of Ramon and concluded that neurons are discrete cells. So with this background, we are able to use graphs as analytical tools for studying brain networks. Okay, so now let us move deeper into the brain networks. The ways in which we have to identify the nodes. This is the crucial role in relating any real-time application to graphs and the way we define our edges. There are multiple ways in which you can relate a graph to a brain network. The most common ways in which we can relate is we divide the given brain network in terms of functional regions into multiple regions in terms of the functions they perform. Say, for example, we divide it into regions called frontal lobe, motor cortex, sensory cortex, and so on, where you can see that frontal lobe is the one, it is a particular part of the brain which is responsible for performing functions like executive functions, thinking, planning, organizing, and so on, which is helping us to emote and so on. So like this, based on the functions performed by different components of the brain, we are dividing the brain into different regions. And then, so what is the advantage of dividing it into regions? We are not going to look at our network in terms of neurons. Each region is again a composition of neurons which are interconnected. So we are no more discussing our network in terms of neurons, but we are going to discuss in terms of regions which are defined in terms of the functions they perform. So now, I think at this all functional regions. And how these functional regions are identified, we have certain atlases which are available in the literature, and there are benchmark atlases as well. So we can map any, each atlas will divide, because we cannot have a unified definition or unified partition of our brain network into multiple regions. It depends on our requirement, like for what purpose we are analyzing the brain, that makes the difference. So there are multiple atlases which divide a given brain network into multiple regions. Say, for example, there is one atlas which divides it into 104 regions, which divides it into 52 regions, and so on. So maybe while you start your study, you can follow any one of these atlases and consider the partition of your brain network into regions on that basis. Now, in our study, we are not getting into such number of regions and so on. So what we are going to have is, we have already divided our brain network into different regions obtained based on the functions they perform. And each such region is going to act as a node for us, right? So with this understanding, we are now going to define what is a brain graph. A brain graph is basically, as the name suggests, it is a graph representation of a brain network. So what is that representation exactly? We are going to represent a brain graph by the symbol G, which is again an ordered pair VE, where V is the set of all brain regions, that is functional regions. And we can define our edge set depending on the context. As appropriate to the context, you can define your edge set. So we can say that in broad sense, what we can say is, if there are two regions which are functionally related, they have common functions, or the response of one brain region is essential to another brain region to perform a certain function, then we can say that they are related. So in broader sense, we can say if we take all regions as vertices, two regions which are functionally related can be connected by means of an edge. So in that sense, we can define the edges of brain graph on three basic aspects. One is called a structural connectivity, as I told. If you consider your entire network as a network of neurons, basically, as such as a network of neurons, you can take each neuron as a node, and you can consider if two neurons which are interconnected as linked pair of vertices in your graph. That is based on the fiber connection, that is bundle of connections between the neural elements. That is one way in which you can define the edges, or as I mentioned earlier, based on the functional dependence, you can define the connectivity between a pair of brain regions. or we can even based on the causal influences. Causal influences is in the sense, like if, as I told, if the response of one particular region causes some impact on another region, then based on this cause and effect relation, that's what we call as causal influence. Based on this cause and effect relationship, we can even define the connectivity between a pair of vertices. So edges can be, that's what I have mentioned, edges can be defined as appropriate to the context. Now for our discussion, we are going to talk with functional connectivity. Okay. We are going to deal with functional connectivity. Actually, in general, if you take network science, the basic theory which we start with is related to centrality measures. Centrality measures, these are measures which are defined in terms of graph parameters. Once you are converting your network as a graph, centrality measures are the measures which are defined in terms of graph parameters. Thereby, you are able to study the structure of a graph, okay, by using these parameters. Now, I have mentioned a very few centrality measures. There are multiple measures. Just to name a few, I have used a very few centrality measures. Let us start with degree centrality. In a graph, as we have seen, a graph is basically a diagram of dots and lines. So if you take any dot, which we call as node, there are multiple lines which are incident on that. See, here you can see that on the edge or node E, there are lines from B, D, G. Now, if you count the number of lines that are incident on a particular node, we call it as degree of that in graph sense. So degree centrality is basically defined for each node in the graph or each node in the network, and that is nothing but degree of the node. So in what sense this degree will help us to understand the structure? If you say, I have a node which has a maximum degree, let us say we have a node, here you can see that node J is having a maximum degree. That's the highest degree centrality, which means you can understand that this node is related or interconnected to more number of nodes when compared to the other. So this means this node can interact with multiple nodes. So any problem with this particular node will cause a severe impact on the entire network. Say, for example, there is one particular region in your brain which has high degree centrality. If that portion of the brain is get affected due to some problem, then that will cause a major impact on the human. So this is how we are using graph parameters, namely degree. One of the graph parameters, namely degree, in order to understand the impact of one node on the entire network. So we call it as a quantifying measure. It quantifies in the sense it tells you to how many other nodes this is interlinked. Okay. And next centrality is betweenness centrality. This is measured even for a particular node by finding out like when in the entire structure of the graph, there are multiple paths between a pair of nodes. Say, for example, if I take node E and H here, there is one way to reach from E to H. You can start from E, go to G, then you can reach H. Or you can start from E, go to D, D to F, F to H. Like this, there are multiple ways. E to B, B to G, G to H. There are multiple ways. We call all such sequence of vertices and edges as paths, where there is no repetition of vertices or edges. Okay. Now, betweenness centrality, what it does, it will, in order to identify, suppose there is a problem with a particular brain region or in general a node. If any problem is with particular node, then what are all the other nodes that are affected? All those which are connected via this particular node will get affected. So what we want to know is how many such paths this particular node lies on, so that we can say what is its significance in the entire network. Okay, so that can be measured in terms of betweenness centrality. Say, for example, if you take web application, if you are trying to analyze the most tolerant web link we want to see, or the most crucial web link, we want to see on which page to which page all the other pages are interlinked. Okay. Similarly, in terms of brain networks, we can see which brain region is very crucial. If that region lies on multiple paths, then that region is very crucial. Any impact on that region will impact the entire network. So this way betweenness centrality is used. And similarly, we have closeness centrality. Closeness centrality, here we define it in terms of n divided by sigma d of uv. By d of uv, we denote the distance between any pair of vertices u and v. Distance is nothing but, so as I told, there are multiple paths between a pair of vertices. Among all the paths, choose the one with minimum number of edges. That is, we call it as shortest length path or shortest path. So d of uv is nothing but the length of a shortest path between a pair of vertices. Now, on an average, we are trying to see how quickly we can reach every other node from node B. So these are all most important factors when you want to study other networks. Apart from brain networks, if you want to study in general any network, these are all very important measures, like if you want to analyze social networks and so on. Similarly, eigenvector centrality. Eigenvector centrality is precisely, as I told, if you have a graph, you can associate a matrix with that. Especially, you can talk about an adjacency matrix with that. Now, given a matrix, basically your adjacency matrix is a square matrix of order n. So given a matrix, square matrix, we can always talk about its we can talk about the eigenvalues of the matrix. Now, how do you compute the eigenvector centrality of a particular node? Given the adjacency matrix, find the eigenvalues, take the largest of these eigenvalues. Now, for that largest eigenvalue, you can find out an eigenvector. Now, if you have a graph of order n, then your eigenvector will have n components. So now what you can do, each component, that is the ith component of your eigenvector, corresponds to the eigenvector centrality of ith node. Now, what is the physical significance of eigenvector centrality? Unlike a degree centrality, which measures only the number of links associated with a particular node, this not only measures the number of links, that is, it doesn't give you a quantitative measure, but it also gives you qualitative measure. Like if there are 3 neighbors for a particular node, one can be very close to that, one can be little far away from that. These are all helpful in the case of social network analysis and other network analysis. So in such cases, among all the neighbors of a particular node, those which are very close in terms of Euclidean distance or in terms of other distances play an important role. So in order to distinguish vertices among the neighbors of a particular node, we can use this eigenvector centrality. So to prioritize the neighbors of a node, we can use this eigenvector centrality. Now, in the brain network analysis, though we are using these centrality measures as we do it in other networks, the usage in the case of brain networks is little limited. I have just taken a few examples, like which are measured in terms of efficiency. I'll go to this example and I'll explain. So here you can see that there are 7 different figures which are available here. Now, let us look into the first figure labeled A. Here, there are 2 particular regions which are marked as 1 and 2. So here we want to differentiate 1 as one region, 2 as another region. Now, in what way we are handling this brain network with that of a graph, by using a graph? Now, as you all know, even when you compare the network of 2 healthy individuals, they will not be similar. If you take the brain network of myself and one of my another person in the group, you will see that even though both are having similar behaviors, both are quite normal, the networks will not be common. So what we will try to do is, we from the network of all healthy controls, we call them as in medical science, they use the word controls to refer to healthy patients, healthy human beings. So from the network of healthy controls, they study the similar properties which are available in healthy controls. And these properties are then compared with the brain network of any other patient who comes in for analysis. So if you analyze the properties of the network of a patient and compare it with the network properties of a healthy control, you will be able to find out whether there is any mismatch in the network properties. And if you get into the deeper analysis of such properties, you will be able to further analyze whether there is any disorder associated with the human being, or is he perfectly normal, but the values are within the acceptable range and so on. Such analysis can be made. So here you can see that in picture A, we have distinguished two regions, 1 and 2. And in picture B, we are able to see that there are other regions which are connected to node 1 as well as node 2. And here, as I have mentioned in the legend, all our green links mentioned that they are all normal links. All our orange links show that they are abnormal links, and all those which are yellow in color, they correspond to links which are at risk. So like this, we are able to distinguish the edges between pair of vertices in our network graph. Once you convert your brain network into a brain graph, you will be able to distinguish the brain edges connecting pairs of brain regions. Now, probably we can assign weights to edges and so on. So in some way, we can distinguish the edges. So in what way that will help you? Now, as I told, you can say that if from the, let us look into the graph D, here you can see that there is a link between regions 1 and 2. And as per the figure, it's nothing but an abnormal region. So if once you identify that there is an abnormal connection between a pair of regions, what we'll do is we will do further analysis. We will try to do an effective analysis. What is effective analysis? We'll say which one is going to, we will try to analyze what is the direction of flow. Direction of flow will help us to understand what is the direction of disease spread. So if from region 2 to region 1, there is a flow in the link, the link is directed, then we say that the region 2 is causing some effect on region 1. Similarly, vice versa, like other way. This way, once you get to know some information from the network by using these centrality measures, we can do further analysis to understand and get into a proper diagnosis of a particular disease. Now, as you can see, the links can be measured in terms of quantitative, like using degree centrality measures, you can measure like how many other regions are getting affected by this particular region. And you can even get into qualitative analysis, whether suppose there is an abnormal connection between a pair of regions, whether this abnormal connection is too serious, whether it is going to be next categorized at risk or it is at a non-risk zone, all these things can be further analyzed. So this is how people in this field of research, they continue with the analysis of brain networks. Now, to be more specific about a particular disorder and let you know, just give a highlight on how graphs are further used for analyzing a disorder. I've taken one of the common disorders, namely autism spectrum disorder. And we say this is one of the common disorders which is most prevalent in pediatric group compared to the adults. So once you, of course, it is not completely curable, but if you are able to identify that at the earlier stage, you can at least keep it under control. We can do some other therapies so that we can make the person to behave normally, or at least to some extent do his or her regular activities. So early diagnosis is always a better option in the case of autism spectrum disorder, though we do not have a permanent cure. Now, what are the ways in which identify a person to be autistic, especially when they are infants? How can you identify? Obviously, the identification depends on since they are infants, we cannot, or toddlers, we cannot get any response from them. So what we have to do, we have to get the responses through their family members, or like they have to analyze and they have to give you the inputs for further analysis. So what kind of inputs are generally collected? What kind of verbal communication they are doing? So if you are talking to that person, whether that person is responding to you or not, in what way he or she is responding, and whether they are ready to mingle with the social group, whether they are ready to mingle with other family members in the group, or if any newcomer is coming to the family, whether how they are responding. These are all the primary analysis which are done in order to understand whether a kid is autistic or not at the beginning stage. But then again, it is voices. Hello.
Nothing, ma'am. You can continue.
Okay. So in this way, we are able to start our analysis. But that analysis, as I said, you are collecting it from the family members. So in order to proceed further, we are going to effectively, I mean, there are studies which effectively use graphs to do such an analysis, to identify brain disorder. So the basic idea is, as I told, not all healthy controls have similar human network, okay, similar brain network. So we have to do a thorough analysis of networks of different healthy controls, and we have to have data of autistic patients. We have to analyze the network of such autistic patients, and then we will come to identify a set of benchmark parameters to identify, classify a particular patient as autistic or non-autistic. Okay. So in that way, machine learning algorithms are very much useful in this particular field. People are using machine learning techniques in order to study this particular disorder. There are quite a number of research publications which are available in this domain. And one such theory is related to graph kernel. So I'll just give you a brief idea of what is the graph kernel. Basically, you start with the set of kernel is when you are given a non-empty set of points. For every ordered pair of that set, you are able to associate a real number. That's what the kernel value is. How you are associating that real number? We are there is a way in which we can associate any set to a Hilbert space, which is already there, which we call as a restricted kernel of a Hilbert space, and so on. So given a set, we can associate a Hilbert space by means of a function phi. You can have a function phi which can associate this way. Now, using that image value, so if phi is a mapping from x to h, you know that phi of x is an element of your Hilbert space. So Hilbert space, what is its speciality? It has an inner product defined on it, which means some distance metric, some metric which can compare, which can relate to elements in the set is available. So by using the inner product of a pair of elements in the Hilbert space, we are defining the kernel between a pair of elements in your original set. Kernel is basically you are trying to identify similarity between a pair of elements. Now here, our pair of elements are nothing but our brain regions. Now we want to study, so not brain regions, we will be considering them as graphs. So given the network of two different patients or healthy controls, we want to analyze how similar these two networks are. Like you have a network of human being 1 and human being 2. I want to understand the similarity, structural similarity and functional similarity in the network of these two human beings. So in that way, our x and y are corresponding to, I mean, our set capital X is the collection of all graphs, and small x and small y are nothing but a pair of graphs which are available in the entire pool of graphs, and with to which we can associate a metric like this. Actually, there is one of the kernels which is called as random walk graph kernel. Probably I'll explain that, and then I'll, if time permits, move on to another kernel. Otherwise, I'll wind up. So first, a kernel which we call as a random walk graph kernel. Walk is basically, see, all the terminologies in graph theory, if you closely observe, they are coined out of the natural languages which we use in our daily life. What do you mean by a walk? When do we say that you are on a walk? When you move from one point to another point, you say that you are going on a walk, right? Similarly, when you go on a walk, what are the things you'll be doing? When you are fixing one source and another destination, you are passing by multiple places in between. So now these multiple places which you cross correspond to the vertices in our graph. Your source and destination correspond to the pair of vertices between which you define a walk. Okay. So what we are basically analyzing is what kind of communication happens between two different brain regions. This random walk, especially walk, helps you to understand the kind of transmission that happens between a pair of brain regions. Okay, which are the other regions involved in that? All these things can be studied. Why random walk? Now, when you consider a brain network, as I told, it is a very complex network. We cannot precisely tell that there is always a walk from this region to another region, or what is the length of the walk, all those things. Now, what we'll say is, suppose I want to talk about all those, a particular walk of length, say K, I want to understand how many such walks are first of all available. That is, I want to understand, suppose you have done an analysis and you are observing that some specific regions are getting affected, or they have got affected. Now you want to get into deeper analysis. You want to study how many such regions are getting affected in this pattern of human network. Okay, so in order to identify this pattern, we sometimes look into the number of walks which are of a given length. Say I want to study about number of walks of length K, then I can determine this. But the problem here is we cannot precisely tell that there will always be a walk from this node to another node. So once you compare your network in terms of atlases and fix the number of functional regions, let us say 104 or 54 or something, you can, given that number, you can talk about the number of walks of a specific length in that graph. And that too with an associated probability. So random walk is a walk wherein which is defined on a graph, to which there is an associated probability distribution with each vertex. What does that probability distribution stand for? It is the probability that you can have a walk. With every vertex, there will be two associated probabilities. One is called as start probability, another one is called as end probability, initial or starting and stopping probability. Starting probability is the probability that you can have a walk of a specific length or a specific walk with that particular node as a starting node. And what is the probability of having a random walk which ends at this particular node? This probability distribution is associated with the with every graph. We can associate a probability distribution with graphs like this. And basically, in order to talk about a kernel, we need this probability distribution. We need a distribution on the set of elements which we are considering. So having said all this, having this basic setup, now what is mean by a, how are you going to define this random walk graph? So it is something which measures the similarity in the number of walks between two different networks. So I have the networks of two different human beings, or two different patients, or two different healthy controls. Now I want to analyze the similarity in the network pattern of these two individuals. So in order to do that, we are counting the number of random walks. When you count the number of random walks, that can be accomplished by means of random walk graph kernel, which is defined in this form. So I'll not get into that definition. Now, what is an efficient way to do that? How you are using graph theory efficiently in order to do that? Okay, we have modeled the network in terms of a graph. We have got a brain graph, and we want to measure the similarity in terms of this random walk. Everything is fine. Now, I have a pair of graphs between which I want to make this analysis. Now, what happens is when two networks are so complex, then studying those two independently is highly cost effective. I mean, it is very, very expensive in terms of all overheads. So what we do in such a scenario, our graph theoretic properties are very much helpful. Like if you are familiar with some of the other graphs which are related to a given graph, we can have a product graph called direct product graph, which is defined this way. Suppose you have two different graphs. The direct product graph is another graph which is derived from these two, whose vertex set is the Cartesian product of the vertex set of the two graphs. Say G1 is a graph with vertex set V1, G2 is a graph with vertex set V2. Then the product of G1 and G2 will have its vertex set as Cartesian product of V1 and V2. Okay. And how do you define the edges between a pair of vertices? If you take any pair of vertices x1, y1, x2, y2 in G1 cross G2, they are adjacent if the first component correspond to vertices in G1, second components correspond to vertices in G2. So if the first component vertices pairs are adjacent in G1 and the second component pairs are adjacent in E2, that is G2, Then we join them by means of an edge in the graph G1 product G2. For example, here you can see that there is an edge from 1 dash to 2 dash because 1 and 2 are adjacent in G1, 1 dash and 2 dash are adjacent in G2. Whereas there is no edge between 1 dash and 2 dash, even though 1 and 2 are adjacent in G1, because 1 dash is not adjacent to itself. Therefore, there is no edge between 1 dash and 2 dash. Okay, fine. So this is how we are defining the direct product of two graphs. Among all the product graphs, why especially direct graph, direct product, and in what way this is going to answer our problem of finding random walk graph kernel? Actually, our objective is to find the number of random walks in each of these two graphs. And if you want to perform random walks on both the graphs and count the number of matching walks, number of walks which are similar of same length and so on, doing that independently on these two graphs is equivalent to performing the same operation on the direct product. I need not work on these two graphs independently. Instead, if I find out the direct product, it is enough if I simply work on this one particular graph. I can find out the number of random walks on this particular graph, random walks of a particular length. Why is it so? By the way the graph product is defined, you can understand that you make a pair of vertices in product to be adjacent, provided they preserve the adjacency both in G1 and G2. So whenever there is a pair of vertices adjacent in the product, the corresponding components preserve their adjacency in their original graphs. So traversing a path or a walk in G1 and G2 independently is equivalent to traversing in the graph G1 product G2. So this way, they are using effectively the properties of graph theory in order to understand the structural properties of. So now I need not study these two structures separately. I can just look into their products. Like this, you can have multifold products and so on. This is one of the ways in which they are using graph theory efficiently in order to study about. Especially this study is helpful in autism spectrum disorder, as I mentioned earlier. If you are interested, you can go through the references which I have mentioned here. And even one of my students is also working on this particular domain. And similarly, there are other kernels which are defined by using shortest paths. And there are multiple other kernels which are available for brain networks. Once you define your network in terms of a graph, you can apply these definitions and study the structural properties. So with this, I conclude with the following note. You can understand that graphs play a very significant role in identifying brain disorders. And we can support the, why graphs play a vital role? Because graphs help you to understand the structure of your brain network. Though it is complex, we are not able to get into the brain and read how they are interconnected, how any effect on one region affect the other region. Though we are not able to study them directly by peeping into our brain, we have in terms of images called as fMRI, MRI, and so on. We take those scan images. With the help of those images, some statistical properties are derived, and these statistical properties help us to construct graphs effectively. And with the help of this, we can better study the structure of human network, human brain network. And this in turn helps you to define suitable graph theoretical biomarkers. Like these are all some biomarkers, random graph kernel, shortest path kernel. These are all some biomarkers which help us to do this comparative analysis and end up with diagnosis of specific brain disorders. So these are all some of the basic ways in which we are applying graphs to analyze the structure of a brain network. So with this short note, let me conclude my talk for today. If you have any question, you can please raise the question.
Thank you, ma'am. It was a really wonderful session. Yeah, I hope all the participants got benefited with your lecture. We are receiving so many questions in the YouTube chat box as well as in the Zoom app. Sure. So with your permission, shall we take the first question?
Sure. Yeah.
So the first question asked by Vetrival G. How can we differentiate the brain analysis functions in other products?
brain analysis functions?
In other products.
Okay, is it about other product graphs?
Yeah, it could be that
See,
question, I think.
that's what, as I told, the different methods which we come out, graph theoretical methods which we come out depends on what your ultimate objective is. See, the methods which we propose for one disorder may not be suitable for the other disorder. For example, if you take any brain disorder which is related to neurological problems, say for example, if you're talking about Parkinson's syndrome, if you're talking about, like as I mentioned, autism spectrum disorder, these are all some kind of disorders which are related to neural problems as well, neurological problems as well. So you have to first fix the disease about which you want to study. You have to look into the pathological factors related to that disorder, that is clinical factors related to that disorder. And these clinical factors will form the basis for us to understand which of the product graphs will be suitable for our study. Okay, so this direct product is one structure which has this property. For example, instead of direct product, if I go for Cartesian product, they will not preserve this adjacency relationship as they have in their graphs G1 and G2. Because in the Cartesian product, how do we define? We define a pair x1, y1, x2, y2 to be adjacent if either x1, x2 is adjacent in G1 and y1 is equal to y2, or y1, y2 is adjacent in G2 and x1 is equal to x2. So it doesn't preserve the adjacency relationship as you have in the original graph. It all depends on what is your ultimate objective. And accordingly, you have to choose the appropriate structure. That's why I have mentioned here. You have to come up with suitable graph theoretical biomarkers which are specific to the brain disorder which you are talking about. Okay, so it depends on which disorder you want to study.
So the next question is, what is the functional connectivity in human brain by the use of graphs?
Yeah, functional connectivity. So as I told, if you take the brain images are available in multiple forms. Like as I told, you can have MRI scan images, fMRI images. fMRI images are functional MRI images where you can see the data which is collected as an fMRI will give you in addition not only the structural capturization or structural visualization of your network, it will also give you some statistical measures like correlation measures, for example. In what way one brain region is correlated to another brain region with respect to a specific pathological parameter. Okay, so these entries are available in the brain images which you take. Now from this data, you have to gather the information, and those data are used in establishing the links in your graph. Brain graph, what did I tell you? Nodes you can fix as functional regions. But how do you define the links? It depends on the context. So if you want to give importance to the correlation matrix value, that is correlation metric, then we will be using that as the edge weight. Okay, that will be used as the edge weight.
So our third
and this
question
way
is,
you can relate functional connectivity. Yeah.
Okay, thank you. The third question is the brain system directed or undirected graph?
You can visualize it in both form. So that's what, if you're studying about the causal effect. So I am particularly interested in, suppose I want to know when a human being is acting to a stimulus. Okay, so suppose I want to understand from where this reaction is coming. So which of the brain region is triggering this reaction? And if that understanding or if that analysis is necessary for your study, you will interpret your graph as a directed graph. Okay. So it is related to the disorder which you want to analyze. If you are trying to, especially in the case of analysis related to causal effects, we go with, it is better to go with directed graphs.
Okay. So the next question is, Can we use the graph wavelets in brain disorders?
No, I'm not familiar with that. I have not gone through that
Okay.
so far.
And
No,
somebody has asked.
I have not explored it so far.
Okay. Okay. And somebody is asking, what is the best textbook for beginners to
Yeah.
study the graph theory? Those who want to do the research, join for the research.
Graph theory
Yes.
or graphs and brain networks. Okay, okay. Since I assumed the audience are having basic graph course, I did not mention that, but still, if you want to have basics of graph theory, I would suggest Introduction to Graph Theory by Douglas B. West. Okay, that is one good book. Or if you find that to be little advanced or difficult to follow, you can start with Introduction to Graph Theory by Reinhard Diestel or Bondi and Murthy. Graph Theory and Applications with Applications by Bondi and Murthy. And coming to graphs and brain networks, if you want to know how graphs are being used, and if you want to know the basics of if you want to have a basic understanding of brain networks and its relation with the graphs, as I have mentioned here, the references 2 and 4 are the best suitable books. Fundamentals of Brain Network Analysis by Alex and others, and Networks of the Brain by Olaf Spans. These two are good books to start.
Okay. So the next question is asked by Purnima Agarwal.
Yes.
Since there are only 52 regions in the brain, does this mean that every brain network would be having maximum 52 vertices?
No, see, as I told, we are not fixing the number of regions. Okay. When you start your research study, first of all, you have to decide that, based on that's what everything is related to what study. The study which you perform for one particular disorder is not similar to the one which you perform for the other disorder. So you have to first look into the basic settings required for your research problem. Then what you have to do is, there are multiple atlases which are available. Now you have to fix out of those atlases which is giving you the information required for your study. And accordingly, you will get a mapping of your brain network with those atlases, and thereby you can identify the functional regions. Okay, so it is not that every time you will go with only these 52 nodes. Yes, of course, if you are fixing that as with respect to an atlas, if you are identifying 54 regions or 52 regions, then that will be the number of nodes for your graph. But we don't always fix it as 54, 57 or whatever it is. It depends on the atlas with which you are comparing. And how to pick up the atlas, it depends on what information you want and whether that atlas classifies your brain network according to the requirement which you want. At least we may not have the exact thing, but more or less there are some benchmark atlases which will help you to analyze further, support your study.
Thank you. And next question is asked by Megha. She asks, how does the music will influence the brain networks?
Obviously, it has its own influence, right? We are getting, like you are listening to music and you are getting into deep sleep. Yes, it has influence, right?
I think what she meant was whether the network structure is going to change because of listening to the music.
It depends on which structure you are talking about. You are talking about structural connectivity. If structural connectivity, it doesn't affect. Functional connectivity, yes, it affects. So it depends on which connectivity. Initially I was discussing about 3 different connectivities, right? Structural connectivity, functional connectivity, and so on, right? So you have to look into which connectivity you want to talk about. Structural connectivity, it is fixed. It is a static network. Functional connectivity, it is getting affected.
Yeah, thank you so much, ma'am.
Functional connectivity, more than functional connectivity, effective connectivity will be affected.
Right, because of the signal
causal influences. Yes.
Yes. Thank you so much, ma'am. So really, it was a wonderful session. All our participants enjoyed a lot. I think they have learned a lot by attending your session. Hope that many of the young participants will be benefited and they will be motivated to take the research career in this graph theory. So we are really thankful to you for accepting the invitation and to be with us today. So it is really a pleasure for me, especially to host you. Thank you so much.